All right, welcome. Today, we're going to tackle a real classic from the Irodov collection, Problem 1.100. And this one is great because, it seems simple on the surface, but it teaches us an absolutely crucial lesson. What do you do when the forces in a problem aren't constant? This is where we go beyond just plugging numbers into formulas and really start to think like a physicist.
Okay, so let's picture the scene. You're out on a lake, the motorboat is cruising along, everything's fine. And then, suddenly, the engine just dies. The boat starts to slow down, right? But how exactly? How can we predict its motion? To do that, we have to figure out the key force that's acting on it now that the engine's off.
So the problem itself gives us a massive hint. It says we should assume the only force that matters is the resistance from the water. And here's the really important part. This isn't your standard simple friction. The problem states that this drag force is directly proportional to the boat's velocity. And that makes sense, right? The faster you try to push through water, the harder it pushes back on you. That relationship is the key to this whole thing.
So here's our mission. We're given the basics on the left, the boat's mass, m, its starting velocity, v0, and the rule for that resistive force, F equals negative RV. And our job is to find three things. First, how long does it take for the boat to stop? Second, how does its velocity change as it covers distance? And third, what's its average velocity over a specific chunk of its journey?
Now, before we write down a single equation, let's talk about a super common trap. If you've just come out of an intro physics class, your first instinct, your gut reaction, might be to reach for those old trusty kinematic equations, like V equals U plus AT. But I'm telling you, for this problem, they are completely useless, and we need to understand why.
Here it is, the fundamental difference. Those simple formulas on the left. They only work when acceleration is a nice, constant number. But look at our situation on the right. Our force F depends on the velocity v. So as the boat slows down, v gets smaller, which means the force F also gets weaker. And a changing force means a changing acceleration. And the second you see a changing acceleration, you have to bring out the big guns, calculus.
So what's our starting point when the simple equations just won't cut it? We always go back to the most fundamental principle of dynamics, Newton's second law. F net equals ma. This is the master key. It works for any force, whether it's constant or, in our case, variable.
Okay, let's just put the pieces together. The net force on our boat is just that water resistance minus RV. And we know that acceleration, A, is really just the calculus way of saying the rate of change of velocity, or dv/dt. So we just substitute those into F equals ma, and we get this. This is called a differential equation, and solving it is the key to unlocking this entire problem.
All right, we've got our master equation. Let's get to work on the first part of our mission, figuring out exactly how long it takes for this boat to come to a complete stop.
To find the time, we're going to use a standard calculus move called separation of variables. It sounds a lot fancier than it is. We just shuffle the equation around to get all the velocity terms, the v's, on one side, and all the time terms, the t's, on the other. Then we just integrate both sides from our starting point, time 0 and velocity v0, up to some later moment. And when you work through that integral, this is the beautiful relationship that pops out. This equation is telling us something really profound. The boat's velocity doesn't decrease in a straight line. It decays exponentially. This function can tell us the boat's exact speed at any moment t after the engine goes quiet.
And right here is where we hit a really surprising, kind of weird result. The question is, how long does it take to stop? Well, that means we want to find the time t when the final velocity v is 0. But just look at our equation. The only way for that right-hand side to become 0 is if that e to the power of something term becomes 0, and an exponential function only gets to 0 when its exponent goes to negative infinity. And for that to happen, time t has to be infinite.
Whoa, wait a second. An infinite amount of time? That can't be right, can it? We've all seen a boat coast to a stop. It doesn't take forever. So did we do the math wrong? No, but we have to be careful and think about what our mathematical model is really telling us about the real world.
What this model is saying is that the boat's speed keeps getting smaller and smaller. It loses half its speed, then half of what's left, then half of that, and so on, forever. It gets infinitely close to 0, but it never technically reaches it. It's called an asymptotic limit. Now, in the real world, of course, other little forces would eventually bring it to a dead stop. But according to the strict rules of this problem, it coasts forever, always moving just a tiny, tiny bit. All right, let's move on to part B. This time, we don't care about time. The question wants to know the boat's velocity as a function of the distance it's traveled, and this is going to require a slightly different mathematical tool.
So how do we get time out of our equation and get distance, or s, into it? We use this incredibly clever trick with the chain rule from calculus. We can rewrite acceleration, a, in this new form, v times dv over ds. Honestly, this is a super useful technique to just file away in your physics toolbox. Anytime a problem asks you to relate velocity and position, this is your move.
So we go back to our good old F equals ma equation, but this time we plug in our new expression for a, and notice what happens. We now have velocity v on both sides of the equation. This is fantastic because it means we can simplify things and create that direct link between force, velocity, and distance that we've been looking for.
So we cancel a v from both sides, we do another integration, and we get this much, much simpler result. And look at that. Unlike the weird exponential decay we saw with time, the boat's velocity decreases linearly with distance. If you were to draw a graph of velocity versus distance, it would just be a perfectly straight, downward sloping line.
And with that nice, simple linear equation, finding the total distance is now a piece of cake. We just ask ourselves, at what distance s does our velocity v finally drop to 0? A little bit of algebra, and we get the answer. The total distance is finite, even though the time to get there was infinite. How cool is that? That's just a fascinating result of the physics here.
All right, on to our final task, part C. Here, we need to find the mean, or the average, velocity, but not for the whole trip, just during the specific time it takes for the boat's speed to drop by some factor, which the problem calls eta. Now, don't let the Greek letter eta scare you. Just think of it as any number, like 2 for half the speed, or 3 for a third of the speed.
And remember, the definition of average velocity is super simple. It's just the total distance you traveled divided by the total time it took. To solve this, we need to find both the distance covered and the time it takes for the velocity to drop from v0 down to v0 divided by eta. And guess what? We already did all the hard work. We have the exact equations we need from parts A and B.
We just take our velocity versus time equation from part A to figure out the time interval. Then we take our velocity versus distance equation from part B to find the distance traveled in that time. We feed both of those into our definition for mean velocity, delta s over delta t. And after a little bit of algebra, we arrive at this final expression.
So, we've solved all 3 parts. But after all that calculus, what's the real lesson here? The specific answer to Irodov 1.10 is way less important than the method we used. What you've just seen is a blueprint, a strategy for solving a whole class of problems that involve variable forces.
This is the process you need to remember. First, always analyze the forces. Are they constant or do they change? If they're variable, your starting point is always F equals ma. Next, you got to choose the right tool for acceleration, a. If the problem is about time, you use dv by dt. If it's about distance, you use v dv by ds. From there, it's a calculus problem. You separate and integrate. And then finally, maybe the most important step, you step back and ask yourself, does this answer actually make physical sense?
And I'll leave you with a challenge to really test if you've got this down. You have the blueprint now. So, how would your entire solution change if that resistive force wasn't proportional to v, but to v squared? Which, by the way, is a much more realistic model for air resistance on a car at high speeds. The setup is the same, but the calculus will be different. Give it a shot. Thanks for working through this with me.